So the other day I was reading a paper with research that I was doing which involved segmenting the lungs from a CT scan. And I found this GitHub profile here from a guy named Sergey Primakov. So shout out to whoever you are from Maastricht University. And he had written a paper in Nature Communications. By the way, Nature Communications is a very highly reputable journal. And I noticed in the article that he actually provided the code from his project where he segmented the lungs publicly, and it's actually right here, and you can take a look at it. And this is state-of-the-art stuff, and he's using all the modern Python libraries to take basically a 3D CT scan and just return a mask of the lungs. And so that's what we're going to look at in this video. If you enjoy this video, please remember to subscribe as always, join the Discord server as well. And finally, I just started an Instagram account for this channel as well, so check that out. Anyways, enjoy. So the packages today are kind of important. We have NumPy and Matplotlib as normal. But the main image processing stuff that is state-of-the-art in Python that we'll be using is scikit image. Is a beautiful image and processing package. It's got a little bit of machine learning stuff. Scikit-learn is the machine learning library associated with it. And then also SciPy. We have some stuff from the ND image library, which is going to allow us to do make measurements of the image, compute center of mass of various regions, and some other functions that we'll get into in this video. So the first thing is we're going to do is we're going to open our data. I've put this data in the Git repository, so you should be able to access it. It's just one directory back. In the data repository, it's a CT scan, and we'll look at it. And so here I just load it using NumPy. And the first thing to do, and this is something I do always when I'm doing machine learning with images or any sort of array that I open, the first step you should always get used to is looking at the shape of the image, because this will tell you about what you just opened. So I have no idea what to expect here. Well, actually I do, but you might not have any idea what to expect. And you see the shape is 263 by 512 by 512. And the shape is the shape of the image. And so what you have here is not a 2D image, but a 3-dimensional image. And so what it is the 263 is along the height of the person. So from 0 to 263. And then the 512 by 512 is like you're taking slices of a person sort of like this. It's called an axial slice. And so you have a 512 by 512 image and you have 263 of them. And they're sort of like a sliced ham of a person. So we'll look at that. And so what it means is we're looking at a 3D image. And what we want to do is we want to process all of these slices. And I'll let you know what our goal is pretty soon. So let's look at a slice of the image. Here I'm going to take the 170th slice of the CT image. And you can see that our image is here. And what you're looking at here is, well, at the bottom you have the table. And it looks like this. And so the table is sort of whatever 500 is. And then it's sort of an air gap in the center of the table. And then you have like a slice of a person sort of directly like this. It's like you cut someone up like a ham. And you're looking in here, and what you have is the 2 lungs, and then you have all the tissue on the outside. And you have this sort of arbitrary scale, and you might not know quite what it is, and we'll get into that. So the first thing to do, we're looking at a new type of data. We should probably understand what the scale means. And so the units correspond to Hounsfield units. And a Hounsfield unit at every point xy, so each pixel value has a Hounsfield unit quality. So I give an xy, you'll tell me how many Hounsfield units it is, and that's the value given by the color bar here. It's equal to 1,000 times whatever the attenuation coefficient is at that location in space, minus the attenuation coefficient of water, divided by the difference between the attenuation coefficient of water and air. And so you might think, well, why are you using this scale? This seems a little bit bizarre. And there's also the linear attenuation coefficient, which is defined such that if I have a beam of intensity I naught coming into a material of length x, the intensity coming out is going to be I naught e to the negative mu x. So it's how many photons get attenuated in the matter. So the higher attenuating this is, the higher the probability that an X-ray shining through your body gets absorbed by your body. So these higher regions here correspond to higher probability of attenuation. And it's sort of scaled like this. And so the reason they define it like this is it gives a really nice scale for differentiating between different types of tissue. So here I have, for example, air is minus 1,000. That's just something you remember. Fat is minus 120 to minus 90. And then you got soft tissue, 100 to 300. You have all these different values for bone, blood, and sort of all this stuff here, and you can determine exactly how many Hounsfield units something is. So looking at this image, you can look at a particular color, and it tells you something about what material the actual point in the image is made up of. So maybe there's bone. Here in the lungs, you can see it's close to -1000 because the lungs are mostly air. The same thing on the outside, and the table is pretty attenuating, so it must be made of some sort of metal. And then there's sort of an air gap in the center. And so we're going to do image processing on this image, and our goal is going to be to look through all the slices. So here I'm looking at the 170th slice. There's also the 160th slice, and I can sort of go through all those slices from all the way from slice 0, which this is the legs of the person. You can see the thigh bones here on the table, all the way to the last slice of the image, which is probably going to be the head and the shoulders like this. And you can actually see the skull like this higher attenuating region here, and then the shoulders and the shoulder bones. What we want to do is we want to get a mask of the lungs in the person. We want to take this image and we want to find a corresponding 3D array where 1 means you're inside the lungs and 0 means you're not. This is getting a lung mask from an image, and of course it's not going to be easy to do, because you can see that if I wanted to segment the lungs like this, that's what we're doing, it's segmentation here. There's all this stuff in the center of the lungs too, and then maybe there's air out here, and how do we differentiate between air and all the other regions? And so I'm going to show you how to use all these libraries to do a fairly complicated task. The first thing we'll do is we'll create a threshold mask, and so we're going to use -320 Hounsfield units as a lower limit. So this just gives us an array of Boolean values. I look for all the pixels where the image is less than -320 Hounsfield units, which if I look up here, -320 is around here. So that'll sort of select out the areas with air. That's sort of like a preliminary step to segmenting the lungs. And we'll go through a bunch of steps like this. So this just gives me an array of trues and falses, and I can set that equal to something called mask. And of course, then I can plot a slice of this mask at 170. So you see that all the air is in yellow here like this. It's true when you're less than -320 Hounsfield units, which is getting close to air. So you can see the lungs are segmented, the background is all air here, that's segmented, and I can go through various slices. I can look at mask 160, it's sort of the same thing here. I can go to mask 10, it's segmenting all the air in all these various slices. So that's our first step that we're going to do to segment the lungs. Of course, here you have some air pockets, and we'll deal with those. So here's the lungs here again, and now we're going to use the clear border function. This is one of the functions that we actually imported up here from scikit image segmentation. And what that's going to do is it's going to clear this outer border of, in this case, true values. It's a Boolean array. So what we want to do is we want to apply this for all the slices in the image. And so we're going to use np.vectorize here. And this will come up a few times in the video. What we're doing is, if you look at the shape of mask, mask.shape, we have a 263 by 512 by 512 image. We want to do this segmentation. We want to remove the border for each of these 2D slices. So we want to loop through all 263 slices and apply clear border to each one of them. So in order to do that, I use numpy.vectorize, which automatically creates a loop over whatever I feed into here. The issue is that mask is a 3D array, and we want to loop over 2D slices. So what we tell the function in vectorize is we say, look, the thing that I want you to loop over is going to be a 2D array. And it will know, it'll say, okay, now I know I'm only looping over the first axis, and I'm going to apply these to 512 by 512 slices. That's sort of how you give a signature in np.vectorize. I'll make a video on this in the future because np.vectorize is a very powerful function. But if you have a 3D array and you give np.vectorize, it's going to try to call this on every element of the array. You don't want that. You want it on every 512 by 512 slice of the array. And for that, that's why you have to give this signature of saying we're giving it a 2D array and it's returning a 2D array in this clear border function. So I'm vectorizing clear border, which takes in a 2D array and it returns a 2D array. And I feed in this 3D array mask. It's going to do it for every slice in the 3D image, which is the mask, and it will return a corresponding 3D array where I've applied this function to each slice of my array. And so I can do this, and then I can look at the mask, the same slice here, and you can see that it's taken this outer border and it's removed it. And that's exactly what we have here. So now we're going to do a little trick. We have the lungs, but you can see that the table also showed up. That's because the table kind of looks like a lung. And you might think, well, no, it doesn't. But to the computer, it's basically a hollowed out region of air surrounded by high attenuation coefficient. So the table is a real pain actually for our challenge. The reason why it's a pain is in some slices, if I compare the area of the lung to the table, the lung is going to have a larger area than the table. But if I look at a different slice, for example, here, so here the lung might have a larger area than the table, but in a different slice, for example, this is part of the lung, but it's clearly smaller than the table. So what we want to do is we want to create different regions for each of the separate volumes in this image. That's going to be the first step to just selecting the lungs. So for example, this might be region 1, region 2, region 3. And for this, we have the label function, which we imported from scikit image.measure here. It's going to take a Boolean array where you either have ones or zeros, like this, and it's going to take each separate distinct region and give it its own integer value. So what I'm doing is I'm calling it on the 3D array mask. Remember that mask is a 3D array still. And I'm saying, okay, you're going to apply this function label. It works on 2D slices. It's going to work on each 512 by 512 slice. It's going to loop over all these slices and return a corresponding 3D array, which is mask labeled. And so I do this. And you can see that I have different regions here. And I'll give a little color bar just to show what's going on here. So you can see that, like, for example, this has the integer value 7. This has the integer value 6. There's a few other little areas that you can see here that have also been segmented. And the table's like this. So I have all my regions in the image given separate integers. And that allows me to differentiate between, okay, this is lung 1, lung 2, the table. I now have integers corresponding to the different segments of the image. Now, the reason I'm doing this is because I want to keep the largest 3 areas in every slice. So I can delete these little areas here and these little areas here. And I'm going to keep lung, lung, table. And you might think, well, why would I do that? Why would I keep the largest 3 areas? Well, remember, I'm doing this for all slices. And like I said before, in some slices, one of the lungs is bigger than the table, for example, in this slice. But in another slice, maybe down here, you're at the bottom of the lung is going to be smaller than the table. So we'll deal with the table later. But the purpose of taking the largest 3 areas is I just want to get rid of any little areas. The table will be left, but it will guarantee that I keep the 2 lungs and then also, unfortunately, the table at this point. So how are we going to do that? Well, the first thing we need to do is we need to compute the areas of each of these separate regions. And so the way you do that, and I sort of go over that here. So here I'm taking a slice. That's basically the slice that I have plotted here. So that I call that slice. Slice is a 2D array. And then I can use this function called region props, which I imported above. Region props is from scikit image.measure library. So what region props will do is it'll give the properties of each of the regions in this slice. So I have 7 regions of this slice, and region props is going to give me the properties of these. So I can, just going through this slowly, here's my slice. My slice is a 2D array. My 2D array is separated into different regions here. And if I call region props on this slice, I have, a list, and then there's different properties for each of these regions. And if I want the area of each region, for example, I can call, for example, here's my first region prop. That corresponds to the region for the integer 0, for example. And I can call dot area. It will give me the area in pixels of this particular region of this slice. So I'll iterate through all the region props. Remember, I have an array like this. So I use list comprehension. I take r.area for each of the r in the region props, and that gives me my areas. So here I can set region props is the region props of the slice. I get my areas. I can look like this, and I have my areas of all the different slices in pixels. I have this sort of larger area, and then these 2 sort of smaller areas here. And then what I'm going to do, remember, this is the areas. I'm going to take the areas from smallest to biggest. So index 3 is 2. This is the smallest area. Remember, 0, 1, 2, 3. This gives me my smallest index. 4, which corresponds to this here, 0, 1, 2, 3, 4. 5 is the second smallest, and then 34 is the next, then 35. And you can see that the indices are in order. And then what I'm going to do is I want from largest to smallest. So I'm going to take this backwards. That's why I give the 2 colons and then -1. So 0 is the largest area. Then 6, 9900 is the second biggest area. So these are my list of my integers in order of biggest to smallest area. So I have these indices, and now I'm only going to consider the 3 largest areas by looping through the indices. So the first thing I do is I create a new slice, and I make it all zeros, and I make it the same shape as slice. So my new slice, for example, here, this is just dot shape. It's a 2D array. It's 512 by 512 for now. I'm going to loop through these indices, which I found above like this, and my new slice, here's it gets a little tricky. I take my region props, which I have here, region props. I take my ith region prop. So for example, here, I could take my 0th one. The 0th region prop corresponds to the largest area. So I go like this. I can get the coordinates of this area like this. So here's my coordinates. Now, I want to get this in a way that I can index my new slice. So I want to index my new slice, which I created. And I'm going to take out all these indices. I'm going to set it equal to 0 or 1 or whatever the index is. So here I have my things, but in order to do this, I need to transpose it like this, and then turn this into a tuple like this. So now I have sort of indices that I can index another array. Then I take my new slice, which is 512 by 512, and I can index using what I created here. And now I have all my values at these points. And if I want to set this equal to a particular value, I'm going to set it equal to I plus 1. So here equals I plus 1. Well, here I don't have I defined, but I could set it equal to 1, for example. And now I can plot.p color mesh my new slice. And you see that I've taken this region and I've set all the values equal to 1. And I'm going to do that for the 3 largest areas here. So I create my new slice. I go through the indices corresponding to the 3 largest areas, which is going to be 0, 6, and 5. This, and this. Each setting them to the corresponding separate, distinct integer. And that's what I do here. And I don't have my indices defined. I have to run this, and this. And then I can plot my new slice. And you can see that I have 3 different regions here, each with its own color. And I've removed all the smaller little areas. Again, we went through a lot of code there. You should sort of go through this slowly, break it apart like I did, and I think you'll understand exactly what's going on here. So now what we're going to do is we're going to do this. We did this for one slice. We want to do this for all the slices in our image. So here's a function called keep top 3. It's basically a summary of all the code we did above. We create a new slice, which is the same shape as the old slice, set equal to 0. I take the region props for that slice, the areas and the indices, and then I loop through the indices corresponding to the 3 largest areas. And that new slice, which is all zeros, I set each of those equal to integer values like I did above. So this takes in a slice, the old slice, which has all the different areas on it, and it returns a new slice, which corresponds to separate integer values, the top 3 areas. Because I have a function that does this, I can then vectorize it like I did before. Well, keep top 3 only takes in a 2D slice. That's how I defined it here, top three areas. Takes in a 2D slice, but I'm feeding it a 3D array called mask labeled. And again, vectorize, if I didn't give it the signature, it would try to go through every element of the 3D array. But I'm saying, no, I want you to take in a 2D array and return a 2D array. And that's what you're vectorizing here. You're vectorizing a function that takes in a 2D array. And so it's an NM to NM. That's 2D array in the signature. And it takes in mask labeled. It's using the keep top 3 function, and I get a new mask labeled array. And then, for example, this is this slice here, and it does it for all the different slices. So all the different slices, I have these top 3 areas like this. The next thing we're going to do is we're going to fill in all these small holes in the lungs. They're kind of gross, and it's easy enough to do with these functions. So first of all, I'm going to turn this back into a binary array where I just have separate areas. In order to do that, I just create a mask, and that's where mask labeled is greater than 0. And of course, if I plot.p color mesh this, again, this is a 3D array. This is not going to work, but I can give it the 170th slice. And now you can see it's just a Boolean array of 1s and 0s. And what we're going to do is we're going to fill in all the little holes of this Boolean array, which is just trues and falses. For that, I use this ndi.binaryFillHoles function. Again, it's a function that takes in a 2D image that has 1s or 0s, and it fills in the little holes. This is sort of what the image looks like. And I'm vectorizing it so it does it for each slice in the 3D array mask that I give it. Because remember that mask is still a 3D array, and I want to apply this to every single slice in that 3D array. So I create my mask, And then I vectorize this operation, which fills in the holes. So this is the function I'm vectorizing, binary fill holes. Again, if I wanted to, I could just call this function on a slice of the mask, like mask 170. If I can type here, mask 170, and it will do this automatically. But here I'm saying, okay, I want you to vectorize this function, and I want you to do it over the full 3D mask, but only on 2D slices, 2D slice by 2D slice. So it'll go off the first axis there of mask. So mask.shape, it's going to do it for all 263 elements. So I get my mask, this will fill in all the holes, and I can plot.color mesh it. And you see that I've gone from an image that has sort of holes in the lungs up here, and now the lungs are nice and filled in. Now, in some slices, actually, you end up taking the trachea, and it's sort of annoying. So if I look at this, for example, here, sort of, I'm above the lungs, but I'm looking at a slice corresponding to the trachea, and I have a hole here, and I don't want that hole. So we need a way to remove the trachea. So it turns out that in a 512 by 512 CT scan, the trachea typically takes up less than 0.69% of the area. So what we do is we delete all areas that have less than 0.69%. So again, I can use my region props function to take all these separate 3 biggest areas and delete any areas that are less than 0.69% of the total area of this slice. So here's my function that removes the trachea. I take my slice, and C, which is the sort of amount of the area that it needs to be less than, is 0.0069 times the total size of the image, 0.69%. So here's my new slice. I copy the original slice of the 2D array, a slice like this. Then I label the slice. This is like what I did before. So I label the slice. So each of the separate areas will have their own label to them. Then I get the region properties of each of those labels like before. So there's 3 different areas here because I've enforced that it's only the top 3. So I have here, it will give me the properties of each of these 3 regions. I get the areas like I did before. And then my indices now are going to be, well, I want to look at the location where these areas are less than C. So 512 squared divided by the areas, that's sort of the percent of the image. And if it's less than 0.0069, that would be like the trachea, then delete it. So we're getting rid of any small areas here in the image, and that's typically the trachea here. So these are the indices corresponding to each of those separate regions. Then I loop through these indices, and at that new slice, the locations where corresponding to those areas, we set those equal to 0, and I return the new slice. So going through this slowly, here's mask -50. I can call the label function on mask -50 like before, and I get this. So I have region 1, region 2, region 3. Then I call my region props on this like before, and it should be an array of size 3 that gives me the properties of each of these 3 separate regions. I can then get the separate areas for each of these regions. And then I can look at the areas. And you can see that one of them is big. That's the table. The other 2 are small in total area of pixels. Those are the other 2 regions. And then I can look for the indices where the area divided by 512 squared is less than 0.069, which is the percentage of the image that we're using as a cutoff. So if I look at this, we'll see is 0.0069. It says that at indices 1 and 2, this holds true. And then I loop through these indices in my new slice, set it equal to 0. So these areas are manually going to be set equal to the background value, which is 0. And then I'm left getting rid of any small areas in this image. So here's my function. I vectorize this function because, again, I'm going to pass the full 3D mask in, but I'm only operating on each 2D slice of the image. And it will return. Remember, it takes in a 2D slice, it returns a new 2D slice. It's going to do this for all 263 slices and return a corresponding 3D array. And so now I have a new mask. And if I look at this, you can see that my trachea is indeed removed in the slices that I want. And everything else before is like normal. So now it's time to remove the table, and we're going to use a clever little trick here to do this. Now, you'll note that each of these separate regions has its own center of mass. This is something from physics. And you could think of all these little pixels as being like little mass elements. So this center of mass might be here, this center of mass might be here, and then there's one here. So what we're going to do is we're going to delete the area that has the lowest center of mass in Y. That's sort of one way to think about this. So let's take an example. So here's my labels like I got before, and I can plot.colorMesh, the labels, like this, and we can compute the center of masses for each of these separate regions. So I can call the center of mass function. I'm going to take one of these regions. So if I look at the plot.colorBar here, you can see that this corresponds to the integer 3, this is the integer 2, and this is the integer 1. The purple is 0, the background. So what I'm going to do is I'm going to say, okay, let's look at the binary array where labels equals 3. I can plot.pcolorMesh this. Remember, this just gives a Boolean array. Labels equals 3 is a Boolean array, so it'll be 1 or true here and then 0 everywhere else. So I can color mesh this, and it gives me this thing here. From this 2D slice, I can compute the center of mass. And it tells me where it is in Y and X. So 185 in X, 273 in Y here on this image. So now we have the delete table function. It takes in a 2D slice. First thing we do is we copy the slice, then we label it like we did above. The slice is going to come from the mask, and so it's going to be either 1s or 0s. We'll label it to have separate regions like this. We'll take the unique indices that are not equal to 0. So we go labels, the np.unique of the labels here, but indexing from 1 onwards because we don't want to take the background. Then we'll compute the center of mass for each of these separate regions. And then what we do is we loop through the corresponding index, so whatever value is given to that region, and the center of mass for each of these things. And I say if the center of mass in Y is less than 30% the height up here, delete it. So that will delete the table. And then also if the center of mass is greater than 60% the height, delete it. The reason for that is sometimes you get the nasal bridge, which has air in it as well. So you get a little air pocket up here. So that will delete any nasal bridge sort of thing here, just to keep the lungs. And so I can run this function. We can create a new mask from our old 3D mask. Then we can look at our new mask, and as you can see, the table is deleted, and it is deleted for all slices here. So this is beautiful. We have a 3D mask of the lungs. The final thing we can do is we can take these lungs, which are segmented, it's almost exactly where the air is, but we can grow them by growing the border a little bit. And for that, we use the binary dilation function. That takes an array of 1s and 0s, and it expands the border of the areas just a little bit. And it depends on the number of iterations you use. So here I'm using 5 iterations. We'll use this on our mask new. So I'm going to feed in mask new here. And I can plot this, and you can see that the area will be just a little bit more expanded. So that gives a little more leeway so that your mask just sort of not only takes in the lungs, but it's a little bit bigger as well. So finally, we'll create a 3D image in Plotly. And now this is a very resolute image. So what we're going to do is we're going to reduce the quality by about 40%. The way to do that is using the zoom function. So that's what I imported from the ND image library. Right here. I imported the zoom function. What that will do is it will take an image and it will reduce the quality by 40%. So that means that the resolution decreases. So instead of being 512, maybe it's 200 and something. And so that's what I do, and I get this image here. So now if I look up the shape of my image, you'll see that it is no longer 512 by 512, but it's shrunken by 40%. So it's the same sort of thing here, you just lose resolution quality of the image. Then we're going to get arrays of X, Y, and Z. So in a CT scan, by the way, the X and Y distance here, so in the 512 by 512, is about 1/4 the size of the distance between separate Z slices. So in order to manage that, I create arrays of X, Y, and Z, and I multiply Z by 4. So if I look at the actual arrays, so the X goes like this, Y goes like this, and Z is in steps of 4. This is going to be for plotting in Plotly. I can create a 3D mesh grid out of these three things. Again, I have a video on this function. So then what I do is I create a 3D plot in Plotly, which I can then open in an HTML browser. And so the data in this is going to be go.volume. I feed in my mesh grid here, and I make sure to flatten each of the mesh grids. So the mesh grid, of course, is a 3D array. And if I call flatten on it, it will sort of go like that. So this is what it originally looks like. I also feed in my image here, making sure to transpose it a little bit so that it fits the right dimensions for the image. I make sure to flatten this as well. So all of these are 1D arrays, and I can save it. And so here, by the way, I had to open the HTML file in Edge. It seems like Edge can do this better than Chrome, so points to Edge there. But I opened up this interactive HTML from Plotly, and as you can see, we have the two lungs segmented beautifully. And of course, the main purpose of this video wasn't quite the visualization at the end. This is more just a tool for me to show you like all the slices at once. But the idea is that once you have a mask of a region of interest, it could be a lung, for example, in a scan, it could be the heart, it could be any picture where maybe you have a car and you want to segment the car. You can do things with those masks, right? You can multiply, for example, if I multiplied the whole CT image by this mask, if I go back here and I multiply, where's my mask? That is my final mask. Nope, it's called mask new. Well, what happens if I multiply mask new times my original image? Let's look at that here. My original image is just called image, I believe. Yep. If I take my mask new and I multiply it by image, I get a new image. So I'm going to call this image new. And then I can plot.color mesh this, my image new, and I'm going to take the 170th slice because that's where the lungs mainly were. And I spelt it wrong, plot.p color mesh. And you can see that now our whole image is basically sort of ignored on the outside, and then we're really just focusing in on the lungs here. So masks are really useful for things like this. And if you're training an AI model, for example, maybe you want it to ignore everything on the outside and just focus on the lungs. Well, masks are a beautiful way of doing this. Anyways, I hope you enjoyed this video. If you made it to the end, hopefully there's a few things that you got out of this video for your own research. Remember to subscribe if you enjoyed this video, and I'll see you next time.